Hello everyone, this is Adithyan. Today we are going to see about logic gates and some other topics. What are logic gates? Logic gates are the basic building blocks of any digital system. It is an electronic circuit having one or more than one input and only one output. The relationship between the input and the output is based on a certain logic. Based on this, logic gates are named as AND gate, OR gate, NOT gate, etc. AND gate. The AND gate has the IC number 7408. The AND gate performs a logical multiplication commonly known as AND function. The output is high when both the inputs are high. The output is low when any one of the input is low. A circuit which performs an AND operation is shown in the figure. It has n input and one output. This is the formula for AND gate. This is the logic diagram of AND gate, where A and B are inputs and Y is the output. The truth table shows that when both the inputs are 0, the output will be 0. When any one of the input is 1, then also the output will be 0. When only both inputs are 1, the output will be 1. OR gate, IC number 7432. The OR gate performs a logical addition commonly known as OR function. The output is high when any one of the input is high. The output is low level when both the inputs are low. This is the formula for OR gate. This is the logic diagram of OR gate, where A and B are inputs and Y is the output. As you can see from the truth table of OR gate, when even one of the input is 1, the output will be 1. And when both the inputs are 0, the output will be 0. NOT gate, IC number 7404. NOT gate is also known as inverter. The output is high when the input is low. The output is low when the input is high. This is the formula for NOT gate. The logic diagram of NOT gate will be like this. Truth table. As I have said before, when the input is 0, the output will be 1. And when the input is 1, the output will be 0. It will be inversed. Next comes the NAND gate, IC number 7400. The NAND gate is a concentration of AND and NOT. The output is high when both inputs are low and any one of the input is low. The output is low level when both inputs are high. This is the formula for NAND gate. And this is the logic diagram for NAND gate. You can express it in both the forms. As you can see from the truth table, when both the inputs are 0, the output will be of high level. When any one of the input is high level, the output will be high level. When both the inputs are in high level, the output will be 0. Next comes the NOR gate, IC number 7402. The NOR gate is a contraction of OR NOT. The output is high when both inputs are low. The output is low when one or both inputs are high. And this is the formula for NOR gate. Logic diagram of NOR gate. As you can see from the truth table, when both the inputs are low, the output will be high. When any one of the input is high, the output will be low. And when both the inputs are high, the output will be low again. Next is the XOR gate, IC number 7486. The output is high when any one of the input is high. The output is low when both the inputs are low and both the inputs are high. And this is the formula for XOR gate. Logic diagram of XOR gate will be like this. From the truth table, we can see that when both the inputs are low level, the output will be of low level. When both the inputs are of high level, the output will be again a low level. Only when any one of the input is of high level, the output will be of an high level. Next comes the XNOR gate, IC number 7410. The output is high when any one of the input is high. The output is low when both the inputs are low and both the inputs are high. And this is the formula for XOR gate. And this is the logic diagram of XOR gate. The truth table shows that when both the inputs are of low, the output is high. When both the inputs are of high level, the output is still high. When one input is high, the output will still be 0. First we will see the simulation for AND gate. When both the inputs are 0, the output will still be 0. When any one input is 1, the output will still be 0. When both the inputs are 1, the output will be 1. Next, moving on to OR gate. When both the inputs are 0, the output will be 0. When any one input is 1, the output will be 1. When both the inputs are 1, the output will again be 1. Moving on to NOT gate. When the input is 0, the output will be 1. When the input is 1, the output will be 0. Next comes the NAND gate. When both the inputs are 0, output will be 1. When any one input is 1, the output will still be 1. When two inputs are 1, the output will be 0. Next comes the NOR gate. When both the inputs are 0, the output will be 1. When any one input is 1, the output will be 0. When both the inputs are 1, the output will still be 0. Next comes the XOR gate. When both the inputs are 0, the output will be 0. When any one input is 1, the output will be 1. When both the inputs are 1, the output will be 0. Next comes the XNOR gate. When both the inputs are 0, the output will be 1. When any one input is 1, the output will be 0. When both the inputs are 1, the output will be 1. Previously we saw the simulation of logic gates. Now let's move on to half-adder and full-adder. Half-adder. A half-adder is a combinational circuit. It needs two binary inputs and two binary outputs. The input variables designate the AND and add-end bits. The output variables produce the sum and carry. The half-adder can be implemented with an exclusive OR and an AND gate, and IC 7408 or IC 7432. Let's see the truth table of half-adder. Inputs given A, B. When both the inputs are 0, the carry will be 0 and the sum will be 0. When B is 1, the carry will be 0, the sum will be 1. When A is 1, the carry will still remain 0, the sum will be 1. When both A and B are 1, the carry will be 1, the sum will be 0. This is the K map of half-adder. This is the circuit diagram of half-adder. Now let's see the simulation of half-adder. From the truth table, when A is 0 and B is 0, the carry will be 0 and the sum will be 0. When A is 0 and B is 1, the carry will be 0, the sum will be 1. When A is 1 and B is 0, the carry will be 0 and sum will be 1. When A is 1 and B is 1, the carry will be 1 and sum will be 0. Now let's move on to full-adder. A full-adder is a combinational circuit that forms the arithmetic sum of input. It consists of 3 inputs and 2 outputs. A full-adder is useful to add 3 bits at a time. In full-adder, some output will be taken from X or gate. Carry output will be taken from OR gate. XOR IC number 7486, OR gate IC number 7432. Full-adder using 2 half-adder. The truth table of full-adder will be consists of 3 inputs and 2 outputs, carry and sum. When A, B and C are 0, the carry will be 0, the sum will be 0. When A, B are 0 and C is 1, the carry will be 0 and sum will be 1. When B is 1 and A, C are 0, the carry will be 0, the sum will be 1. When B and C are 1, the carry will be 1, the sum will be 0. When A is 1, B, C are 0, the carry will be 0 and sum will be 1. When A is 1 and C is 1, the carry will be 1 and the sum will be 0. When both A and B are 1 and C is 0, the carry will be 1, the sum will be 0. When all A, B, C are 1, the carry will be 1, the sum will also be 1. Next is the K-map this is the K-map of fulladder. This is the circuit diagram of fulladder. Now let's see the simulation of fulladder. When A, B and C are 0, the carry and sum will be 0. When C is 1, the sum will be 1. When B is 1 and other are 0, the sum will be 1, the carry will be 0. When both B and C are 1, the carry will be 1, the sum will be 0. When A alone is 1, the sum will be 1, the carry will be 0. When A and C are 1, the carry will be 1, the sum will be 0. When both A and B are 1, the carry will be 1, the sum will be 0. When all A, B, C are 1, the carry will be 1 and the sum will be 1. Previously we saw the simulation of fulladder and halfadder. Now let's move on to Halfsubtracter and fullsubtracter. Halfsubtracter. The Halfsubtracter is constructed using XOR and AND gate. The Halfsubtracter has 2 inputs and 2 outputs. The outputs are difference and borrow. The difference can be applied using XOR gate. Borrow output can be implemented using an AND gate and an inverter. AND IC number 7408, XOR IC number 7486. The truth table Halfsubtracter is like this: input A, B, output borrow difference. When both the inputs are 0, the outputs will be 0. When B is 1, borrow will be 1, difference will be 1. When A is 1, borrow will be 0, difference will be 1. When A and B are 1, the borrow will be 0 and the difference will be 0. This is the K-map of Halfsubtracter. This is the circuit diagram of Halfsubtracter. Now let's see the simulation of Halfsubtracter. When A is 0 and B is 0, both the borrow and difference are 0. When A is 0 and B is 1, the borrow is 1 and the difference is also 1. When A is 1 and B is 0, the borrow is 0 and the difference is 1. When A is 1 and B is 1, both borrow and difference are 0. Okay, now that we have seen the simulation video of Halfsubtracter, let's move on to fullsubtracter. The fullsubtracter is a combination of XOR and OR NOT gates. In a fullsubtracter, the logic circuit should have 3 inputs and 2 outputs. The two Halfsubtracter put together gives a fullsubtracter. The first Halfsubtracter will be C and B. The output will be difference output of fullsubtracter. The expression AB assembles the borrow output of the Halfsubtracter, and the second term is the inverted difference output of first XOR. Let's see the truth table of fullsubtracter. There are 3 inputs A, B, C, outputs borrow difference. When all the inputs are 0, borrow and difference is 0. When C is 1, borrow will be 1 and difference will be 1. When B alone is 1, borrow will be 1, difference will be 1. When B and C are 1, borrow will be 1, difference will be 0. When A alone is 1, difference will be 1. When A and C are 1, difference will be 0, borrow will be 0. When A and B are 1, difference will be 0, borrow will be 0. When all are 1, borrow will be 1, difference will be 1. And this is the K-map of fullsubtracter. And this is the circuit diagram of fullsubtracter. Now let's see the simulation of fullsubtracter. When A, B and C are 0, the borrow will still remain 0, the difference will also remain unchanged. When C is 1 and A, B are 0, the borrow will be 1, the difference will also be 1. When B is 1 and A and C are 0, borrow will be 1 and difference will be 1. When B, C are 1 and A is 0, borrow will be 1 and difference will be 0. When A is 1 and B, C are 0, borrow will be 0 and difference will be 1. When A is 1, B is 0 and C is 1, borrow will be 0, difference will be 0. When A is 1, B is 1 and C is 0, the borrow will be 0, difference will be 0. When A is 1, B is 1 and C is 1, difference will be 1, borrow will also be 1. Code conversion. Now let's see the topic on code conversion, binary to gray, gray to binary. Code is a symbolic representation of discrete information. Codes are of different types. Gray code is one of the most important codes. It is a non-weighted code which belongs to a class of codes called minimum change codes. In this code, while traversing from one step to another step, only one bit in the code group changes. In case of gray code, two adjacent code numbers differs from each other by only one bit. The idea of it can be cleared from the table given below. As some applications in analog to digital converters and in some input and output devices. Binary to gray code conversion. Binary to gray code conversion is a very simple process. There are several steps to do these types of conversions. Steps given below elaborate on the idea of this type of conversion. The MSB of the gray code will be exactly equal to the first bit of the given binary number. MSB refers here to most significant bit. Now the second bit of the code will be exclusive OR of the first and second bit of the given binary numbers. That is, if both the bits are same, the results will be 0, and if they are different, the result will be 1. The third bit of gray code will be equal to the exclusive OR of the second and the third bit of the given binary number. Thus, the binary to gray code conversion goes on. Objective gray code system is a binary number system in which successive pair of number differs in only one bit. It is used in applications in which the normal sequence of binary numbers generated by the hardware may produce an error or ambiguity during the transition from one number to the next. Input and output variables. The 4-bit combinations assigned to the binary code to gray. 4 bits to represent a decimal digit. There are 4 inputs and 4 outputs. The input variable are defined as B3, B2, B1, B0. And the output variables are defined as G3, G2, G1, G0. And this is the truth table for binary to gray code conversion. Here the inputs are binary and the output will be in the form of gray code. And this is the K-map to convert binary to gray code. And this is the K-map for G0 and G1. And this is the circuit design. Now let's see the simulation for conversion of binary to gray code. When B3 is 0, B2 is 0, B1 is 0 and B0 is 0, then all G3, G2, G1, G0 will remain as 0. When B3 is 0, B2 is 0, B1 is 0 and B0 is 1, G3 will be 0, G2 will be 0, G1 will be 0 and G0 will be 1. When B3 is 0, B2 is 0, B1 is 1, B0 is 0. G3 will be 0, G2 will be 0, G1 will be 1, G0 will also be 1. When B3 is 0, B2 is 0, B1 is 1, B0 is 1. G3 will be 0, G2 will be 0, G1 will be 1, G0 will be 0. When B3 is 0, B2 is 1, B1 is 0 and B0 is 0. G3 will be 0, G2 will be 1, G1 will be 1, G0 will be 0. When B3 is 0, B2 is 1, B1 is 0, B0 is 1. G3 will be 0, G2 will be 1, G1 will be 1, G0 will be 1. When B3 is 0, B2 is 1, B1 is 1 and B0 is 0. G3 will be 0, G2 will be 1, G1 will be 0, G0 will be 1. When B3 is 0, B2 is 1, B1 is 1, B0 is 1. G3 will be 0, G2 will be 1, G1 will be 0, G0 will be 0. When B3 is 1, B2 is 0, B1 is 0, B0 is 0. G3 is 1, G2 is 1, G1 is 0, G0 is 0. When B3 is 1, B2 is 0, B1 is 0, B0 is 1, G3 will be 1, G2 will be 1, G1 will be 1, G0 will be 1. When B3 is 1, B2 is 0, B1 is 1, B0 is 0. G3 will be 1, G2 will be 1, G1 will be 1, G0 will be 1. When B3 is 1, B2 is 0, B1 is 1, B0 is 1. G3 will be 1, G3 will be 2, G3 will be 1, G2 will be 1, G1 will be 1, G0 will be 0. When B3 is 1, B2 is 1, B1 is not 1, 0, B0 is 0, G3 will be 1, G2 will be 0, G1 will be 1, G0 will be 0. When B3 is 1, B2 is 1, B1 is 0, B0 is 1. G3 will be 1, G2 will be 0, G1 will be 1, G0 will be 1. When B3 is 1, B2 is 1, B1 is 1, B0 is 0. G3 will be 1, G2 will be 0, G1 will be 0, G0 will be 1. When B3 is 1, B2 is 1, B1 is 1, B0 is 1. G3 will be 1, G2 will be 0, G1 will be 0, G0 will be 0. That's all. Gray code to binary converter. Gray code to binary conversion is again very simple and easy process. Following steps can make your idea clear on this type of conversions. The most significant bit of the binary number will be equal to the most significant bit of the gray and gray code. Now if the second gray bit is 0, the second binary bit will be the same as the previous or the first bit. If the gray bit is 1, the second binary bit will alter. If it was 1, it will be 0, and if it was 0, it will be 1. This step is continued for all the bits to do gray code to binary conversion. Objective: the most significant bit of the binary code is always equal to the most significant bit of the binary number. Other bits of the output binary code can be obtained by checking gray code bit at that index. Input and output variables. The 4-bit combination assigned to gray to binary code. 4 bits to represent a decimal digit. There are 4 inputs and 4 outputs. The input variable are defined as G3, G2, G1, G0, and the output variables are defined as B3, B2, B1, B0. And this is the truth table for conversion of gray code to binary code. And these are the K-map for B3 and B2. And this is the K-map for B1 and B0. And this is the circuit design to conversion of gray code to binary code. Now let's see the simulation for the conversion of gray code to binary code. Now we are going to check only 4 inputs and outputs to check whether both the solutions are the same. Here we are going to give G3 as 0, G2 is 0, G1 is 0, G0 is 1. Hence the value B3 will be 0, B2 will be 0, B1 will be 0, B0 will be 1. Now again we are going to give a different input. G3 will be 0, G2 will be 1, G1 will be 0, G0 will be 1. Output will be B3 will be 0, B2 will be 1, B1 will be 1, B0 will be 0. And again we are going to give another input. G3 will be 1, G2 will be 1, G1 will be 1, G0 will be 0. B3 will be 1, B2 will be 0, B1 will be 1, B0 will be 1. Now the last input, G3 as 1, G2 will be 0, G1 will be 0, G0 will be 0. B3 will be 1, B2 will be 1, B1 will be 1, B0 will be 1. As we can see that the previous simulation and the values are equal to this simulation. Okay. Now we are going to see about encoder and decoder. Encoder. An encoder is a digital circuit that performs inverse operation of a decoder. An encoder has second input lines, 2n input lines and n in output lines. In encoder, the output lines generates the binary code corresponding to the input value. In octal to binary encoder, it has 8 inputs, 1 for each octal digit and 3 output that generate the corresponding binary code. In encoder, it is assumed that the only input has a value of 1 at any given time, otherwise the circuit is meaningless. It has an ambiguilla that when all inputs are 0, the outputs are 0. The 0 outputs can also be generated when DO equal to 1. Combinational design procedure. An encoder is a combinational circuit that performs the reverse operation of decoder. It has maximum of 2 power n input lines and n output lines. It will produce a binary code equivalent to the input, which is active high. Therefore, the encoder encodes 2 power n input lines with n bits. Objective. The other routine tasks are mentioned on the encoder resume as follows: filling and organizing data, preparing and sorting data, reviewing data, ensure accuracy, entering data from paper to computer systems, completing data backups, filing and making paper copies, checking work for any duplications, reporting to management about errors, and keeping a record of data entry and database information. Truth table. And this is the truth table for encoder. It has 7 inputs and 3 outputs. This is the logic diagram for encoder. Now let us see the simulation for encoder. Just now we have seen the truth table for encoder. Let us check whether our simulation is working probably or not by giving it, for example, 4 values. Let y1 be 1 and the others be 0. The output must be A should be 0, B should be 0, C should be 1. Next, let us give y7 as 1 and the other as 0. The output should be A should be 1, B should be 1, C should be 1. And let us give y4 as 1. The output should be A must be 1, B must be 0, C must be 0. And the last, let us give y6 as 1. The output must be A must be 1, B must be 1 and C must be 0. Since all the values are correct, our simulation is working properly. Next is a decoder. A decoder is a multiple input output logic circuit which converts coded input into coded output where input and output codes are different. The input code generally has fewer bits than the output code. Each input code word produces a different output code word. That is, there is 1-to-1 mapping can be expressed in truth table. In the block diagram of decoder circuit, the encoded information is present as n input producing 2n possible outputs. 2n output values are from 0 through out 2n minus 1. Combinational design procedure. Determine required number of input and output from the specification. Derive the truth table for each of the outputs based on their relationship to the input. Simplify the Boolean expression for each output. Draw a label diagram that represents the simplified Boolean expression. Objective. A decoder is a digital circuit that detects the presence of a specified combination of bits on its input and indicates the presence of that code by a specified output level. A decoder is a circuit that changes a code into a set of signals. It is called a decoder because it does the reverse of encoding. But we will begin our study of encoders and decoders with decoders because they are simpler to design. And this is the truth table for decoder. It has 3 inputs and 4 outputs. And this is the logic diagram for a decoder. Now let us see about decoder simulation. From the truth table we have seen when E, A and B are 0, D1, D2 and D3 is 1. When E is 1 and rest are 0, D0, D1, D2, D3 are 1. When B alone is 1, the D0, D2 and D3 are 1. When A alone is 1, D0, D1 and D3 are 1. When A and B both are 1 while E is 0, D0, D1, D2 is 1 and D3 is 0. Since all the combinations are working properly, our simulation is working perfectly. Thank you.